Hold on. There's not enough on your desk? I didn't pass out 4 of each? Okay. So, hear me very, very clearly on this. Come on, Joel, you've got stuff to learn. Joel, you need a copy of this. I don't usually do this. What I did though is I went in and I took the old test that I used and I shortened it and I printed out a copy of it. Now, please hear me very clearly on this. I don't ever give out the same test twice. That's why it's hard for students to cheat. But the same concepts will definitely be on your test. And the same, not same formatting, but similar formatting will be on your test. This is a great set of problems for you to practice for your test that is on Monday. Please notice on one of the sheets at the top, it says Module 1, Topic 3, Building Polynomials Test Review. Actually, yeah, this was the test review, not even an old test. This is something that you should be able to do everything of because we wrapped this up yesterday. The second one that says Module 1, Topic 2, or Module 2, Topic 1, Characteristics of Polynomial Functions, that's what we're doing today and tomorrow. This is to help you review. I will be posting solutions to these on Friday, and I will have lots and lots of notes to help you study for your test. Take advantage of that resource. Now, 2 things I do want to point at. First off, questions. So will it ever be enough to memorize the answers for this?
No.
Heck to the no. You have to what? Learn. You have to study, you have to learn, but that means you have to understand. You have to understand the how and the why that things work. Now I want to point this out on the back side of Module 1, Topic 3. In order to do the practice for 6 and 7, you have to do number 5. I'm not going to ask you to do number 5 on your test, but this is a good review for stuff we've done in the past. Number 5 says, write a function g of x in factored form that would be the product of the functions given in the graph. Every line here is a factor. Notice what did I just say every factor is? It's a line. Should you know how to create the equation of a line? Yes. If you don't, go Google that crap. Go look at YouTube that I have done time and time again where we have identified the equation of a line and practiced writing the equation of a line. And I will point this out, I had someone who came in yesterday after school who's like, Mr. Kinney, I thought those videos go away. Nope, every video from the beginning of the semester is still online. It's still on YouTube. And it's dated, the early ones have lots of notes in them, but they definitely have a title with what we covered that day. Yes, Kadarius. Literally just search my name, Nathan Kinney. It is the first one that pops up.
Who named you?
My mother? I can tell you more context to it, but yeah, my mother named me.
What's your middle name?
Charles.
Why is that so funny?
That was a funny.
It's just his name.
Your middle name is Charles.
I know. I was like, it's a. Right. Anyway, so right here. So please notice to do number 5, you need to be able to write the equation of a line. To be able to do number 8, what type of factors do you have? Yeah, but what type of functions? Like, what type of factors do we see? A linear and a quadratic. A linear and a quadratic. So you have to know how to write the equation of a line, but you also have to know how to write the equation of a quadratic.
That right there, Miss Kitty. Right there. So, never mind after that.
Okay. With this quadratic, I will point this out. Do you know what the vertex of that quadratic is?
No. C. Oh.
It doesn't look like a pretty number on a vertex.
No.
But do you know what the roots are of that quadratic?
Yes.
So what form should you use? I will use factored form. Don't forget you still have to calculate what A is. Everything else should be pretty straightforward. Okay? But again, solutions will be on Schoology for this so that you can check your work. You can shoot me emails to ask questions. But that's your study guide. Take advantage of it. Yes, ma'am.
Are you going to count like full absences or absences counted from the class itself?
Absences from my class.
And I got about 12 in here.
If they're skills.
Why are we here? Because it is not just to randomly learn a whole bunch of math terminology and mathematical lingo. What are we here for?
Children in the bathroom, but that bathroom got somebody going up there, so you gotta get out.
Okay. That's unfortunate.
Yeah, she was sitting there for
Okay, so why are we here? To learn how to develop arguments. Now, why is the idea of developing an argument important? Why is developing arguments important? Because you've got to learn how to think. Please hear me very clearly on this. You have got to learn how to think. Okay? The idea of thinking is a skill that is something that will follow you for the rest of your life, and I cannot emphasize that enough. I talk to people at the university all the time. I talk to actually one of the higher-ups at Shelton regularly. He goes to church with me, and we were talking last night. I talk with business owners a lot of times, and one of the biggest complaints and struggles is students exit high school without understanding how to think. And if you can't think well, it's really hard to learn on the job. If you can't think well, it's going to be hard to get promoted and make larger amounts of money. So, please understand, I'm not just here to teach you math. I want you to learn math. I think there's beauty in mathematics, but the thinking side is so critically important. That's what's most important here, and that's what we're going to be doing very, very, very heavily today. Now, as a reminder of the way I work, I'm going to ask you to engage in examining patterns and relationships. So I just need you to try to make sense out of what's happening, but afterwards, I always go over it. You need to take the notes, you need to learn from the whole class discussion. So, remember, we're here to learn how to think. Now, the objectives, please note that this is what the activity is from yesterday. We're trying to find the pattern for the maximum number of x-intercepts, extrema, and in behavior of a polynomial just from the equation. You can always graph these things on calculators. But we want to be able to quickly look at the equation and know what's the number of x-intercepts going to be, what's the maximum number of extrema, what's the in behavior going to look like. And over here, right, group 7 was missing. Desiree was not, didn't have everything written down, and so she got, did you put in the calculator to do the sketch up there? So go ahead and put the sketch over there. B through G, because of my, go ahead and do the sketch. Huh? Oh, remember, hit menu and go change your window settings. You'll probably have to change your Y minimum and Y maximum to like -400 and 400. Okay. So, I figured out B through G just because I knew a couple of key ideas. And it ties into the degree, and it ties into the leading coefficient. That's all you have to know every single detail that I wrote up there. And so, we're trying to find the pattern. How do the degree, how do the leading coefficient tell me all of those features? And so you're going to have to identify that pattern, or identify the maximum number of x-intercepts and all those things. And it is fundamentally built out of what key concept? Fundamental theorem of algebra. That is a critical idea. And so, not just reading it off of here. We can all read that the fundamental theorem of algebra states any polynomial equation of degree n must have exactly n complex roots or solutions, but those roots may be multiple roots. What does that mean?
Whatever the degree, that's how many roots there are.
Whatever the degree is, that's how many roots there are. They could be real or they could be imaginary. They could have a multiplicity of 1 or they could have a multiplicity of 2 or 3 or 4, and we're going to continue to look at what that means. So here's what we're doing, right? We talked about it. What's the degree of a polynomial? How do I know what the degree is right here? The highest exponent, highest power. So it's what? It is an exponent, or degree of 3. Pretty sure there's supposed to be a 2 there. And I think, was it a plus or a minus here, Lily Kate? 2x to the 4th plus 2x cubed?
It was like 2 of them.
If I didn't write it yesterday, it was supposed to be.
Yeah, it is plus.
Okay. Trying to look for my copy of it. Yeah, 2x, which one did y'all have? X cubed, it was minus 4x squared. And then 2x to the fourth plus 2x cubed. Okay, those were what those functions were supposed to be. That's my degree, and then how to identify that leading coefficient, because that's what we're trying to examine today. It is the coefficient of the highest power, right? So what is the constant that's multiplied there? So we've already done this. We've written down our answers. Please make sure that you have your answers written down for A through G. Does anyone not have their answers written down for A through G? Right, they should be on the board. If you have not finished writing them down, let's take maximum of 2 minutes. Write down all of A through G. We need to move quickly though. We got stuff to do today.
This is on the same sheet of paper.
No, on the sheet of paper I gave you all at the end of class yesterday. Remember it says higher power on it? That one that Lily Kate has right there? It's not. It's right there in Jacoby's hands. He's in your group.
Okay, Mr. King.
Sit down. Keep your hands to yourself before I have to write you up. You must be outside your mind. I missed it, but I saw you.
You must be outside your mind.
Actually,
Okay, we've got about 60 seconds left before I continue.
Why did you just kiss me?
I don't even have legs.
Wait, no. Just your answers. Guys, don't write down all the answers, just your answers. Right? So you should only be looking at your responses because you should have your equation down, you should have a sketch down. I do want to point out two quick things while some of us are still writing down. If you look around the room, how should we write our x-intercepts? We want it as a point, right? So make sure you consider that. Another thing is, I know it's harder on the whiteboards, on the chalkboards, but I saw a couple of students, or obviously we have kind of sketches here. What are the key things that you should make sure you have correct on your graph on your paper? You have to pay attention to what? The zeros, and what else? Maybe the y-intercept, but more than that for me, just where the function is positive and negative. That's the main thing. I will point out that your max and min are good points to pay attention to as well. You have a graphing calculator, but the most important points that will be things I'm looking for on your test are your x-intercepts, your zeros, and I will be looking for you to have the correct positives and negatives. All right. I'm actually going to change this equation just slightly. I'm going to make this a negative 3x squared. So looking at this, right, so just as a quick reminder, because we're going to use this in a second, so what would be the degree of that quadratic? That would change this graph completely. It's fine. It's going to look something like this. Okay, the degree is 2. I meant to update that yesterday. So degree 2, how many x-intercepts? 2 x-intercepts.
Yes.
How many times does the graph turn? 1 turn. What is the leading coefficient of the polynomial? It's what? Leading coefficient is -3. So as your graph goes farther and farther to the left, what happens vertically? The left side, y is approaching what? Negative infinity. How do you know that? It's not going to stop what? Going down, right? As we go to the left, it goes down. Right side, as it goes to the right, y is approaching negative infinity. Now, I didn't show you this part yesterday, but I do want to formalize something. Notice we said y is approaching in negative infinity for both of these. What is x approaching? If it's going towards the left side, What's x approaching? Negative infinity. Right side, x is approaching positive infinity. Right? As x goes to the left and as x goes to the right, this is the full notation for in behavior. When you are ever asked for in behavior, that's how you need to write it. Once you get to calculus, you'll learn a different notation called a limit. I'm not worried about that right now. In Algebra 2 and in pre-calculus, that's how you should write in behavior every single time. Not necessarily always the same infinities, but as x approaches blank, what is your y approach? As x approaches blank, what is y approach? And so here, the ends of the graphs go in the same direction. And so here's what we need to do at this point. Math is the study of what? Patterns and relationships. What we're going to do is called a gallery walk, where you walk around and you look at the responses that everyone has come up with. And the only thing I need you to think about, and so you do have space at the bottom for the gallery walk, the question A, how do you determine the maximum number of x-intercepts a polynomial has using the equation? What about the number of terms? So the first gallery walk we do, all I want you to focus on is how can I figure out the number of terms and figure out the number of x-intercepts based on the equation. There's a pattern there. Okay? Then we're going to do a second gallery walk after that, where we will be looking at B and at C. Alright? So, let's get up. I want you to start with where you were. I want you to look at your set of answers, and then about 45 seconds in, I'm going to have you rotate. You don't have to perfect this yet. You need to find a pattern or relationship, and you won't find it until you get pretty far along. But start to develop hypotheses. I believe blank, that's a claim, but have evidence for it. Talk about it within your small groups. So let's get up, move to your answers that you originally had, and let's start to look for a way to answer A. Let's get up, and let's move. Okay, we have 45 seconds to try to find some relationship between, or some relationship for how we're figuring out the number of x-intercepts and the number of terms. Alright, let's grab a seat and let's talk about it. I want to formalize a couple of notes to ourselves.
Yeah.
So, here's something that I want to point out. Okay? Two things I want to point out about this before we continue. First off, we have already talked about it. Remember, in the objectives, well, first off, let me remind you, what is mathematics? Patterns and relationships. That's what I need y'all to engage in. Some of these conversations are not super related to the mathematics, which means you are not going to notice the patterns and relationships, which means we're not thinking, which means we're not growing and learning. I need you focused. And so please notice the language here for A, because it says, how do you determine the maximum number of x-intercepts? The maximum number is what? Come on, y'all just told me.
The highest degree.
Matches, not the highest
Or the
degree.
maximum.
Matches. I'm going to push back on that language a little bit because we keep just messing up a little bit. You don't have to say highest degree. What do you need to say?
Degree.
Degree, because what is the degree?
The highest.
The highest power, right? You don't have to say highest degree. The highest power is the degree. The maximum number of x-intercepts matches the degree. Why do we have to say the maximum though? Why can't we just say the number of x-intercepts is the degree?
take some of the imaginary.
Some of what?
Zero.
Some of the zeros, some of the roots could be what? Imaginary. Can someone open the door, please? Some zeros could be imaginary. Thank you. All right. What could some of those zeros also be? Double or triple, right? So some zeros could be imaginary or have higher multiplicities. Something with a higher multiplicity, we would count that zero multiple times, but we would only have one x-intercept. That's why we have to say the maximum number of x-intercepts matches the degree. The mathematical language there matters. That is a proper understanding of the concept. We have to say the maximum number. And then what was the hypothesis we came up with about the number of terms, the number of extrema? It's going to be one less term than the what? Okay, someone said something a little bit different earlier. The number of what? X-intercepts. So here's what I want to push back on, I want to show you. So think about this. Just looking at this, does anyone know what the degree of this would be? Third degree, how do you know that?
Double root.
We have a double root right here, so that counts as how many zeros? 2. I have a single root here, so that's how many? 3. So that degree is 3. How many turns does it have though? Or how many x-intercepts does it have? 2 x-intercepts, because remember, the maximum number of x-intercepts is the degree, but how many turns does this have? 2 x-intercepts and 2 turns. And so we need to settle this debate. Is the maximum number of terms one less than the number of x-intercepts?
No.
Is it one less? No. So how do we determine the maximum number of turns? The degree. It is always one less than the degree. Look at the different answers around the room. Third degree, how many turns? 2. Fourth degree, how many turns? 3. Third degree, how many turns? 2. Fifth degree, how many turns? So notice the maximum number of turns is one less than the degree. Okay? Maximum number of turns. And also, I will point this out. I don't particularly love this mathematical language here. If you've heard me say it, I like to say, not I like to, the more mathematically precise word is extrema. What does that word extrema make you think of? Extremes, right? What are the extremes going to be? They're going to be your highest, which we also call the maximum, and the lowest, which is called the minimum, right? And really it's called an extremum. That's singular from the Latin root. Extrema is plural from the Latin root. So we're talking about your max and mins, right? When we talk about the terms, we're talking about the maximum, we're talking about the minimum. That's where the graph is turning. So the maximum number of turns is what?
Is one lesser than the
Than the degree. Remember, that's what we just looked at around the room. It's not necessarily based on the x-intercepts, but it is based on the degree. The maximum number of turns or extrema is one less than the degree.
So would you prefer us to say extrema?
I would prefer that term extrema. I will accept the word turns, but when you get to higher level mathematics like pre-calculus or anything else, they're going to talk about maximums or maxima and minima or extrema instead of terms. So to be better prepared for that later course, you want to be aware of the language they'll use there. Okay. Now, we need to get up, we need to do a second gallery walk. Okay? So the question that we are looking at right now is what determines if the end behavior of the graph is the same or if it is different? Which answer choice was about end behavior being the same or different?
G.
G, right? So I need us to get up, go back to your boards, look at G, and let's try to find a pattern now about when will the end behavior be the same, will it be different? So go ahead and get up, move back to your group.
I think it's coming first.
Get up, let's move.
But I don't know
Come on. We need to get up, we need to move. Here you go. So, we are now trying to look at when is the end behavior the same and when it... Hey, already seated. We should already have walked to our groups and grab the seat. So, when I look here at B, what determines if the end behavior of the graph is the same? End behavior is the same when, what did y'all come up with in our groups?
when it's even.
When what's even? Don't say that word. It's the highest power, which is the degree. You can say either highest power or you can say degree. I would be looking for that word degree. So that end behavior is the same when the degree is what?
I'm sure, man.
So let's look again around this room. Let's check it. That degree over there is even. The end behavior is the same in green.
How do they have a negative term?
What?
They have a negative term.
Who got negative terms?
We know.
Oh, they put D and then dash and then they put a 3. Talking about the purple one?
Okay, yeah.
Yeah, that's all that they did. It's not a negative number of terms. I can definitely see where that confusion is. When I look at the purple there, that degree is even, and the end behavior was the same. Over here, this end behavior, or this degree was even. The end behavior was the same. So is that a pattern that holds up for all of these functions? Yes, Desiree, headphones out. B then, continuing. When is the end behavior different?
When the degree is odd.
So it is different when the degree is odd. And we can check that around the room. And guys, I want you to understand something. I don't need it to be perfect. I just needed y'all to develop ideas. Right? Earlier, Naisha came up with the idea that when it's a third degree, then the end behavior is always different, right? Yeah. And when I heard that idea, I asked you a question, and I pushed back on it to help her and her group think about it some more. And so I just need you to engage because I can ask you the right questions to help you think more and understand more. And then we'll formalize at the end. That's what I need you doing. And if you ever have friends that have me in the future, you need to tell them, engage and think, and Mr. Kinney will ask you the right questions to help you understand more if you are focused on your learning. And then we will have a whole class discussion afterwards every single time. I'll teach it. But I need you to engage in the patterns and relationships first. That's how you learn, ladies and gentlemen. You notice a pattern or relationship. You then investigate it and you test that evidence that you came up with. And then if that evidence continues to hold up time and time and time again, you probably have the right idea. That is how you grow and learn on your own because you will not always have a teacher. You've got to learn how to think. You've got to learn how to learn. Now, we're going to talk about a couple of things before we actually answer C. Actually, here's what I'll do. So I want to point this out. When we look at our end behaviors around the room, so if it's even, they could go the same. And that means it could go up to infinity on both sides, or it could what? Go down to negative infinity on both sides. So this would be even, this would be odd. So when it's odd, the end behavior is what? Different. So what determines whether with an even it's going up or if it's going down for that end behavior? Let's glance around, let's look at it as the same, or look together. So notice, y should be approaching infinity, that's going up here, and y approaches infinity. So here, with this even, they're both going up. When I look at, where's the next one? When I look at this even, these are both going up to positive infinity. But when I look at this even, y is going towards negative infinity, meaning going down. So what's different, right? How are we figuring out when that function is going both up or both down for an even degree? What's the pattern there? Negative what? Which coefficient? There's a lot of coefficients. So what's that? The coefficient with the highest, with the degree called?
The leading coefficient.
Leading coefficient. So this leading coefficient is negative, and the end behavior goes down towards the negatives. I definitely see where you're going with that. But no, I'm just saying, guys, if the leading coefficient is negative, the end behavior goes down towards the negatives. Here, even, and the leading coefficient is positive, and the end behavior goes up. So how will the leading coefficient affect the end behavior? So if we have an even degree, and the leading, I'm going to use LC for leading coefficient. We good with that? How would I indicate if the leading coefficient is positive using mathematical symbols? You could. So it's something in respect to 0 to be positive. Is it equal to 0?
Oh, that little thing, the little arrow.
The little arrow, what's that called?
Arrow.
No. It's what? Greater than. If the leading coefficient is greater than 0, that's what kind of number? Positive. And so the end behavior goes up to the positives. If the leading coefficient is less than 0, the end behavior goes down towards the negatives. And so we have to notice, first off, that end behavior. So this is something you could write under C, right? And I would sketch out those graphs to go with it, the even degrees versus the odd degrees. The leading coefficient determines if they're going up together or down together. If it's even though, that degree, or if it's even, the end behavior has to be the same. And then the leading coefficient tells us if they go together up or together down. So I would sketch out those graphs, I would make the note about even degree, and when the leading coefficient is positive versus negative. So, go ahead and get a sketch of your odd degrees and we'll talk about how to figure out what the end behavior looks like in a second. Okay. So one thing I will point out is on the surface, the odd degrees seem a little bit harder, but there's a really quick tell. So if you look at this one, which I actually just erased it, it looks something like this. Okay? So what's the leading coefficient for this one right here? Positive or negative? Positive. And it looks like that, right? When I look over here, I don't see the equation. Oh, leading coefficient for E is negative. And you see how it's going in the opposite direction. Okay? Here's what I would point out to you. Does anyone remember what the lowest odd degree is? The lowest odd degree. Lowest odd degree.
Oh, what?
Linear functions. You see how that linear function has the same end behavior? What would the leading coefficient or slope be for that line? So the odd degrees act very similar to the linear functions. So if you can note, hey, that linear coefficient is positive, it's like a positive sloped line. That's how I would figure it out. So the leading coefficient is greater than 0. So like a line with positive slope. So the leading coefficient is positive there. So what about this one? Sorry, y'all still writing. So what about the last graph? What's the leading coefficient going to be? Negative, like a line with what type of slope? That's it. I want you to hear me very clearly on this. I'm going to ask you to write the end behavior as x goes to negative infinity, y approaches blank. There is way too much there to memorize all of it though. But can you sketch what the function is going to look like to make sense out of it? 100%. So when I did this for group 7 over here with this function, I knew what my end behavior would be simply because what type of degree is it? Odd. What type of leading coefficient is it? Positive. So I don't know exactly what this graph looks like. It would be something wild like this. But what I did to figure out the end behavior is I drew in my mind a positive sloped line. That's how I knew on the left-hand side the y was going down to negative infinity. That's how on the right-hand side I knew the y was going up to positive infinity. I just pictured a line to figure out that end behavior. So if you can sketch out, either in your mind or better yet, to show me evidence of your understanding on assessments, that line to show the end behavior, you can very quickly figure out the end behavior. And so again, I will make this note. This is not the entire, like this notation would be fine, left side, y approaches negative infinity. But what I would really want to see is as x approaches what? On the left-hand side.
Negative infinity.
As x goes towards negative infinity, y is going towards negative infinity. And that's how you read it, is going towards or approaches. On the right-hand side, as x goes towards infinity, right? X is going to the right, the function is also going up. Those are details that I would expect you to note and see. we answered all of, we have, with our answers, because we did them together, we have already answered everything in the quick notes, so maybe on the back side of higher powers where it has quick notes, make a note to yourself, just see number 2. You were supposed to actually answer those questions for number 2 as you did your gallery walk, but for your quick notes, put C answers under number 2. Okay, work with your small groups. Let's answer numbers 1 through 4 to check our understandings. We're going to have a whole class discussion about it in just a minute, but work with each other, talk your ideas out. Don't let one person dominate the conversation. If you are confused where they're getting their answer, you should ask a question. If you are sharing the answer, check with everyone in your group to make sure they agree and that they understand why. It is the discussion, it's called mathematical discourse, that's going to help everyone grow and learn the most. So work with each other. Let's answer numbers 1 through 4 to check our understandings. All right, ladies and gentlemen, let's talk about these. What we have, remember, is f of x equals a times x to the n plus b x to the n minus 1 plus ... plus c. And yeah, there's unknowns there, but we should know things about those unknowns based on our graph. So, I need people making claims and providing evidence for those claims. I need you to listen and see, do you want to add on to or do you want to push back on? And I need you to ask questions if you are confused. That's how you grow and learn. So, number 1, true or false, n must be odd. True? Okay? Does anybody want to push back on that claim? Everybody's good with that claim? So what's the evidence that you developed to know that n must be odd? Okay, but why did Jacoby say it's 5? That actually goes into number 4. What about the intercept?
X-intercept is 5 points away. 1, 2, 3, 4, 5.
Okay, so let me ask you this. Would this have to have an n that's odd? Wait, hold on.
It's odd.
Is it odd?
No.
Why not?
Oh, no, it's gonna be 6.
So we would want to notice in this case that we have a double root. So even though there's 5 x-intercepts this time, one of those x-intercepts is a double root, and there's something else that we are missing right now. Is there anything else? Say again. Okay, the number of turns is how many? For the one that was originally given? 4, which would indicate that the degree probably is 5. Okay, there's something else.
Oh, the looking at one. It's gonna be positive. It's negative.
What am I looking at right now? I'm trying to figure out the degree, but I'm looking at, like, what am I referring to right here? The n is known as the in behavior. And what does this in behavior tell me? What should I notice about my in behavior? It is different. And if that in behavior is different, what does the degree have to be? Odd, yes. More than likely, yeah, it has 5 zeros. However, the biggest thing we've got to notice is that in behavior is different, right? In behavior is different. So n has to be odd. I've already referred to it, 4 turns. for extrema. So, probably 5th degree. And how many x-intercepts? 5 x-intercepts. So, probably 5 zeros. Right, there's no double roots or anything else like that. And so, but that is something we would want to notice is the degree is the maximum number of x-intercepts, right? That is a small detail we need to be careful about. The degree is the maximum number of x-intercepts. Man, I didn't realize it's supposed to rain like that today.
I'm so glad.
Is that because you don't have to do softball? Number 2, true or false? A is greater than 0. False? Okay, first off, does anyone want to push back on that? Anybody want to ask a question about that? So, what do we mean by A? Right? And so, Lily Kate, I know you're talking about like there's these unknowns here, there's variables here, right? But we do want to notice A simply means the leading coefficient, right? N was my degree, A is my leading coefficient, and so y'all don't think it's greater than 0, meaning you think it is false, right? You already said that, so you think A is less than 0, what's your evidence?
The line is a negative slope.
Yeah, if I look at that in behavior, right? First off, again, that in behavior is in different directions. It has to be an odd degree. But if I think about it in terms of slope, what type of slope would that be? A negative slope. Because it's a negative slope, that has to be a negative leading coefficient. Right? I do want to clarify, we're not looking at slope. But I can use that line to help me recognize that the leading coefficient has to be negative. A lot of us A lot of us seem to be stuck on number 3. Anybody find something to help us figure out number 3?
You get a 1%.
Yeah, the y-intercept. How did you know to look at the y-intercept?
Let's see the 1%.
Oh yeah. Notice C is a constant. If I think about a y-intercept, what's true for every y-intercept that's ever existed?
It's equal to 0.
The x is equal to, and so everything here that has an x to it is going to become a what? And so I'd just be left with C. So does the y-intercept have to be greater than 0? How do we know that? Above the x-axis, right? So true, right? C is referring to my y-intercept, which is above x-axis. So, number 4, N must be 5. True? True. Anybody want to push back? I do. N is probably 5. But what could we have?
Oh, a decimal. No.
Not a decimal. We could, well, not a double root, but, because remember it never touches and bounces away, but if it's a triple root, it'll actually also go through, right? If it's a quintuple root, meaning 5, it'll also go through. More than likely, none of them are. What other types of roots could you have that increase the degree, but we would not see as an x-intercept? A what? Imaginary, right? So it is technically false. N is probably 5. but could have roots with higher multiplicities. Or imaginary zeros. Say again. I should have brought my rain jacket apparently. I don't do umbrellas, but I love the rain jacket. Alright. I don't know why. So here's something I want to point out. You have another sheet of paper on your desk that I passed out with this. We do not have time to do this. This is your homework assignment tonight. Guys, look at it. Someone's freaking out when all it is taking everything we just did and putting it in a chart. Yes, we gotta learn how to go through our notes, right? So an even degree with a positive leading coefficient. Give an example.
You gotta stop my guy.
Now, please hear me clearly on this. When I say an example of a polynomial function, I'm talking about an equation here. The graph would be what we put here. Okay? And so I will remind you, what could you use at home to help you get a more accurate graph shape? I would use Desmos. Yeah. I just said Desmos. Yeah, that's it. Okay, same thing here. Alright, so turn to page M1-96 in your textbooks. You're tired of the textbook? Well, it's good that you only have like a week, right?
Yeah, you missing a I'm missing a lot.
Okay, we don't have enough time to do this in small groups. We're going to have to do this together. I was planning on sending this file out to you, but I do want to point this out, right? On M1-196, so we're using the assignment sent out to the calculators, play around with the sliders to find any patterns. And so, if I remember correctly, got to take open. Yeah, here we go, page 196. So one thing I want to point out right here, okay, each of the functions in these graphs are called what? They're called power functions. Please notice, by the way, I didn't send it out to the calculator, you don't need to log in because we don't have time, we're doing it together. A power function. When we say p of x equals a times x to the n, what does that look similar to? Thank you. Right? When we just looked at those polynomials, it started out as a times x to the n plus b times x to the n minus 1. A power function is simply a polynomial with one term. Right? A times x to the n. Notice that's all it is. It's just that one term. That's what is a power function. And so what we're trying to look at here is think about some patterns, right? Looking here at B, state any observations or patterns that you notice. So here's the calculator. And I want to point this out. So right now, what is my n? Can you see it? 1. N is 1. Now n is 3. Now n is 5. Anybody notice any patterns? They're all odd, okay? So what about when we have an odd degree? What's happening? Think about what we just discussed.
Oh, the end's gonna be different. The end.
Is the odd degree having opposite end behavior? Okay? So now let's look at A. If I change A to a negative, Does that still follow the same pattern we saw earlier? Still different directions, but notice like a negative slope. Okay? So now, here's an even in behavior, or even degree. Do we still see the same pattern? If it's even degree, the in behavior is the same. And when A is positive, the in behavior is going towards the, it's going up towards the, because it's a positive A, so it's going up towards the positives. Remember how I talked about that? Look, A is positive. What's the in behavior doing? It's going up towards the positives. Now, David, I want you to be careful with your language. You just said it's increasing, right? Okay? This is why I want David and I want all of you to be careful. When you read a graph, you read it like a book, meaning from left to right. So technically, David, what's happening here is that my function is decreasing. Does that make sense? Like, I understand you're seeing it and you're like, oh, it's going up, it's increasing. But because of how we read a graph, this is decreasing. It hits the minimum here and then it starts to increase. Does that make sense? Okay? Now, there is another pattern that we do want to notice. We've already talked about the end behaviors. But look at the middle of these graphs. What happens as the n increase? Oh, by the way, if A is negative, it's going down towards the negatives for the end behavior. But look at what happens when in the middle when n increases. Anybody see any patterns there? Look at the middle. What's happening? So line, look at the middle. Look at the middle again. What happened in the middle?
The A's got what?
To go vertical.
It's getting more vertically on the ends, but look at the middle.
And it,
Is it flattening out?
yeah.
Okay. Let's look at the even degrees. As n increases, what's happening in the middle? It's getting flattered. And so here's what we want to make a note of under B, right? Actually, looking here, sketch and label the next two graphs. So notice we have y equals x to the 6th is the last one, right? When I look at the next graph in the sequence, it's going to be y equals x to the 7th. So what do I immediately know from this? Huh? So it's odd, so someone said different. What's different? The end behavior is different. Should it be increasing like this, or should it be decreasing like this? Increasing because the leading coefficient is positive. Okay, so we want to notice that. But notice how it's x to the 7th. What should happen in the middle? It's going to get pretty what? Flat. As the degree goes up, it's going to get steeper on the sides and it's going to flatten out more in the center. Please hear me very clearly. It is not flat. It is still a curve. It just looks really flat. I'm going to show you why in a second. So the leading coefficient is positive, so it still looks like a positive slope, right? But the sides there, the end behavior gets really, really, really steep, and the middle there gets really, really, really flat. And so the next one is y equals x to the 8th. What do I know about this graph? Just knowing y equals x to the 8th. It's going to be, what's the same direction? Okay, so is it going up or is it going down? It's going up because the leading coefficient is positive, so the end behavior goes into the positives. And what's going to happen in the middle?
You're gonna be a little flat.
It's going to be super flat. It's going to be even flatter than what we saw with x to the 7th. Okay? Okay. But be careful, because it's not a line. It just looks really flat. It look like I get it that you're thinking that, but it is still a curve. Okay? It's just hard to see that curve. It looks like a line. Okay? Okay, part B. So what observations or patterns do you notice? So, first off, as n increases, what did we notice? Right, as the degree increases, what are we noticing? Where does it get flatter? Not the line, the curve or the polynomial gets flatter at the center, right? So as n increases, the polynomial, we can say power function, remember that's the type we have here, the power function flattens out more and more in the middle. Okay? And also notice what happened on the sides. It got what? Got steeper. Well, it got wider because of that middle, right? It looks wider, but didn't it get steeper as n increases? So on sides, curve got steeper. It's growing more quickly. So here is why, so this is number 3 on page 199, and this is the last thing we will do today. Here is why. Think about this. If I take 2 and I raise it to the third, what do I get? Actually, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32. Notice for the same input, what's happening to the output as n increases? It's getting bigger and bigger and bigger and bigger. However, if I have 1/2 to the second, I get 1/4. 1/2 to the third, I get 1/8. 1/2 to the fourth, I get 1/16. So in the middle between -1 and 1, as the n increases, this number gets closer and closer to what? 0. So it flattens out more because it gets to that 0 more quickly. That's why that's happening. I apologize that I'm having to sprint through that. Here's something to be aware of. Nope, didn't put it on here. I didn't update that. You do have a short understanding check based on the lesson that was higher powers that we just finished. So you being able to apply the concepts we just did, that's what the understanding check will be on. Remember, the Matthew that was due last night was only Unit 1 from Module 3. Don't go beyond that. Friday, tomorrow, we're going to look at Module 2, Topic 3, a little bit after the understanding check. And test is when? Monday. You have a study guide. Solutions will be on Schoology.
You walked right into it. Are you okay?
Module 3 is the one that I assigned last week.
Let's do all 9.
No, just Unit 1. Yes.
I'm a bit tall.